Welcome to the course on molecules in motion. In the last class, we had talked about, we had done few illustrated with few examples, talked about weak electrolytes. Now, moving further, what we can do is look into the transport properties. We have already talked about the various types of electrolytes. Now, when we have transport of charge, which is carried by the ions in an electrolyte. So, what happens? We have a solution in which we have the electrolyte dissolved, solid electrolyte dissolved, and these dissolved electrolyte will be dissociated into ions and they will be moving as free ions. So, the transport of the charge which is carried by the ions can be interpreted by the amount of charge transported, the amount of charge which is transported by the ion, and also the speed with which the individual's ion move with that particular charge. So, if I have a potential difference which is applied across the two electrodes in an electrolyte, this phi 1 is one electrode potential, this is another electrode potential. The difference between the two is the potential difference across the two electrodes. Then the moving ions in the solution, what is the speed with which they are moving, and that is we say in terms what we are going to look into is to find out the mobility or the speed with which they move. So, moving ions, when you have an ion in solution, what are they subjected to? They are actually having various types of forces acting on it. When the ions are in the liquid medium, that is the solvent medium, the ions are moving under the influence of a potential gradient. Okay? So, what is accelerating them to move forward is if there is a potential gradient, the positive charges are moving to the negative terminal and the negative charges are moving to the positive terminal. So, there is a gradient in potential. The force which is actually driving them is the potential difference across the two electrodes. So, the moving ions is going to reach a terminal velocity or which we call as the drift speed, when the force accelerating due to the potential gradient balances out the frictional force, which is a retarding force. So, we have two types of forces acting on it. One is the force which is accelerating the ions, one ion moving trying to move one ion type of ions trying to move to one type of electrode and another type of ion moving to the opposite electrode. This is the driving force. So, this is going to what is going to accelerate the particle. Now, they are going to be reaching a terminal speed or a drift speed when this force which is accelerating them to move forward is balanced out by a frictional force which is retardant. So, the retarding force and the accelerating force should balance. So, let us first identify what are the types of what is the form of the accelerating force which we have. So, the accelerating force which is we have just now said, it is the driving force is the potential gradient. Okay. We have the electrode connected to a battery system. So, the complete diagram will have a battery system something like this. So, circuit is completed and the movement of the ions through the solution actually completes the circuit. So, what you have, the accelerating force will be due to some electric field which is going to be existing. What is that electric field going to be? It is going to be the potential difference across the two electrodes divided by the length between the two electrodes. So, L is the length separating the two electrodes and phi delta phi, it is the potential difference across the two electrodes. Okay. So, if we want to find out the force of a particular charge, say Z, then what will be the force? If Z is the charge, Ze is the charge, rather we can say charge, the charge is actually the electronic charge, and Z is the number of ions which is generated. So, Ze is the total charge which is associated with a particular type of ion. Okay. E is the charge and Z is the number of ions which is associated. So, Z into E total gives you the total the charge associated with a particular ion. If that is multiplied by the electric field which is applied, okay, whatever electric field which we have existing when we have a circuit completed, that electric field, if you multiply by the total charge is Ze, will give you what? Will give you the force that is exerted on the particle. Okay. So, if I have the Ze as the total charge associated with the ion, it is moving across the electric potential difference of delta phi with the distance between the two electrode being L, then it is going to be nothing but Ze, the small e is the electronic charge into the capital E is the applied force, applied field, that will be equal to the force which is existing on the particle, on the charged particle, that is ion, when it is subjected to a accelerating force generated due to gradient in potential. Okay. And that is going to be, can be represented by something like this. You have the minus as the negative charges and green as the positive charges. So, cations go to the negative electrode and the anions go to the positive electrodes. This is what is driving them. The force which is acting on them, which is accelerating on the particle towards each of the type of electrode, cation to the negative electrode, anion to positive electrode, is nothing but the total charge into the electric field which is existing, Ze into E, right. Now, what is another type of force which is existing, which is we just now said is a retarding force, which is going to drag the molecules or ions which is there in the solution medium into the opposite direction to the way it is it is accelerating towards. Okay. So, the retarding forces which are acting is the drag force, the frictional force due to the friction which is existing between in the solution medium. Okay. If you remember your Stokes law also had a similar sort of expression where you reach the terminal velocity when a particle or a molecule or any object is subjected to a movement in the solution, which is you have the frictional force and the bound force which is supposed to be balanced, and then you reach a terminal velocity. So, when you have a sphere of radius a moving with the speed s, moving through a fluid of viscosity eta, then the viscous drag will be, the force which is acting is viscous drag will be F into S. F is what? F is the frictional factor, S is the drift speed. Okay. So, when you have a say of radius a, we are talking about sphere because we are talking about the ions, and we say that the ions are surrounded by a certain the layer of the solvent ion in such a way that it looks like a sphere. So, we are visualizing the ions in the form of sphere of a particular radius, speeding with a particular speed s, moving through a fluid medium which is having a viscosity eta. So, the dragging force is due to the frictional resistance. So, this drag force frictional resistance, which is actually the viscous drag we talk about, and this viscous drag which is acting on the ions in solution is nothing but the frictional factor into the terminal speed or drift speed. Okay. So, the two forces we have which is acting on the particle, one is the retarding force and the other is the accelerating force. So, these force should be balancing each other to reach a terminal speed or a drift speed. So, if we look at it, if you equate the two, the terminal speed of an ion moving electric field is obtained when the two forces which is acting on the ions are balanced. The two opposing forces which is there is, one is the force which is generated due to the presence of electric field and the other one is the viscous drag. So, this is a frictional factor into S and this is nothing but Z E into the total field. Okay. So, if these are to be equated, then the speed with which they are going to be moving eventually will be known as the drift speed, and that is nothing but Z E by F, the frictional factor. Frictional factor is nothing but from the expression which we have got from Stokes' law, which is 6 pi eta into A. Okay. And the eta is the eta of the viscosity coefficient of the solvent medium which we are looking into. Okay. And A is the radius of this ion which we are. So, if you have the expression given to us for the speed with which the molecules or ions in the solutions are moving is nothing but Z E into the capital E by F, which can be represented if we are substituting the value of the frictional factor, then Z E capital E divided by 6 pi eta A. A is what? That is the diameter of the ion in the solvent. We can call it as the solvated radius of the ion. What is the E? Small e is the electronic charge. Eta naught is the viscosity of the solvent, is the charge of the ion. Now, the solvated radius which we are talking about, this is also known as the hydrodynamic radius when we have the solvent medium as water. Okay. So, we now introduce another term known as the mobility. The mobility is something which is related to the speed of the ions. So, if the new quantity which we define, say this is not something which you observe, this is a expression which we are defining. Okay. So, the drift speed is nothing but the mobility of the ion into the applied electric field. So, what we can say, the ionic mobility U can be represented as S by E, right. The expression of S you know, the expression of E you know. This is the expression of S, Z E capital E divided by 6 pi eta A divided into 1 by E. The E gets cancelled. So, what we are getting here is E will not be there in the expression. What we are getting here is Z E by 6 pi eta A, where S is the drift speed, capital E is the electric field applied, Z is the charge on the ion, eta naught is the solvent viscosity, small e is the electronic charge and A is the solvented radius, right. Now, look at these values, just have a look at the ionic mobility values which I have written down. This is sodium, this is potassium, that is zinc, and this is H plus. The order of the mobility is 10 to the power -8, all of them, but when we are seeing sodium, potassium and zinc, you just have a look at the trend. Zinc is much more than the potassium ion, and while same comparison, just have a look at the value of the H plus ion. The say H plus ion in the solution has a much higher mobility compared to that of the potassium ion or sodium ion or the zinc ion. Okay. Now, when we look at the anions, you just have a look as the type of anions which we have: chloride, bromide, sulphate and the hydroxyl ion. The order of the mobilities are all in -8, 10 to the power -8. The unit is meters square, second inverse and volt inverse. So, if this is the values, you can make out there is a drastic difference between the conductivity mobilities of ions such as H plus and OH minus then compared to the rest of the ions which we are looking into in the solution. Sulphate ion has again a low value compared to the chloride ion. Similarly, zinc ion has a lower value than the potassium ion. So, what is the reason? How do we interpret the values of the ionic mobilities of the various types of ion? So, the drift speed governs the rate of charge transport, and drift speed is what we have just now seen. The drift speed is important because the mobility is directly proportional to the drift speed divided by the capital E. So, if I know the drift speed, and drift speed is nothing but expression something like this, ZE by capital E divided by 2 pi eta and A. So, what are the variables you can see? The variables you can see is in this expression finally, or in this expression also. If I have a fixed value of the electric field applied, then this S, the drift speed, is going to depend directly on the number of charge numbers and inversely proportional to the hydrated radius or solvated radius of the ions, and inversely proportional also to the viscosity of the solvent. So, what we from that expression what we have, that the drift speed is going to be depending, which is, if drift speed changes, directly proportional is going to be the ionic mobility. So, drift speed is dependent on the viscosity of the solution eta, which is inversely proportional to the drift speed. It is also depending on the size of the ion which we are dealing with, because A is the radius which we are talking about. Suppose we have an ion which is bulky, large ionic radii. We see in the previous, if you have larger ionic radii, then you are compared these two. This will be much potassium is much smaller than that of zinc ion. So, this is going to be much heavier ion compared to this, and you will be having a much higher diameter, ionic diameter compared to the potassium. But you see, having higher diameter means it is going to be moving slowly, right, because it is inversely proportional. So, what we have, so the effects which we have, if you have a bulky ion, bigger ion, you have a larger intermolecular or larger ionic radii. Bulkier ion will be having much bigger radiuses, and if you have a bigger radius, then you have lower conductance. Okay. How? The conductivity is again related to the motion of the ions or the movement of the ions. Higher will be the movement, higher will be the speed, higher will be the conductivity. The molar conductivity will increase, right. Now, other ions like the alkali ions like sodium plus, Na plus, these alkali metals, what you have, the hydrodynamic, you just have a look at what we have here: lithium, sodium, potassium, rubidium. These are the alkali metal ions. Okay. What is happening here? We are having, you just see, compared to lithium, which is going to be the smallest, if you have the smallest radii, then you should have the highest speed, because radii is inversely proportional to the speed which we have seen, right. So, if it is smaller ion, you should have a higher speed, but what happens here, you see the lithium conductivity is much smaller than that of the potassium ion. Why is it so? When you have a smaller ion, then what happens? The hydrodynamic radius, the solvated radius is larger. Smaller the ion, bigger will be the hydrated radius because of the solvated ion. Okay. So, other ions like metal, particularly alkali metal ions, the hydrodynamic radius is larger for ionic radius, which is smaller. Okay. So, what we have, this we have hydrodynamic sphere of ions, which moves with the ion when we are moving, when the ion is moving through the solution. Smaller ions have higher charge density than the larger ions, and hence larger hydrated sphere, and hence higher the solvated radius. Okay. So, one thing is, if you have a bulkier ion, if you have bulky ions, their movement is less. So, if their movement is less, then the S speed is less, that their mobility is less, U is less. On the other hand, suppose you have a metal, alkali metal like a series which we have just now discussed. Have a look at this. You have, if you can visualize the periodic table, you have lithium, sodium, potassium, rubidium. These metal ions, if you look at very carefully, this is lithium is the smallest, right. If lithium is the smallest, then there should be the highest mobility, but it is not so, because the smaller the ion is, more will be the charge density over that ion, and more solvent molecules will get attached to it. So, the hydrodynamic radius, or if it is a solvent like water, or the solvated radius or hydration radius of the sphere, which is suppose for the ion, is going to be increased, right. Now, I would like you to remember that when we are talking about the sodium OH ion and the H plus ion, they are having a order difference in their conductivity, or say molar ionic conductivity as such, compared to the other anions or cations we had looked into. So, why is this so? Like H plus and OH minus, they have way far ahead larger values of molar conductance, the ionic mobilities U for that particular system. What is the reason? Like if you have, the ions which is moving in solution, what is happening when you are having an ion? The smaller the ion, higher is the charge density over it, more amount of solvent molecules get attached to it. So, that hydrated volume of the sphere of that ion increases. Okay. And if the hydrated, if the size is increased, obviously that is inversely proportional to the speed. So, if they are going to be bulkier ions, they are going to be moved slowly, and if they are moving slowly, then their mobility will be less, okay, and there will be a decrease in conductance, molar conductance. So, few exceptions are there. If you have the ammonia in ammonium ion in the ammonia solution, they have different values as expected, compared to as expected for the complex more heavy ions. And also suppose we look into only we forget about the OH minus, just look at the H plus ion, then the H plus ion, the conductivity or mobility is much higher than if of the same charge values of other ions like sodium and potassium. Why is it so? What is the basis of explaining that? We explain that on the basis of Grotthuss theorem. What you have, whenever we are talking about an ion which is moving in solution, it is actually the movement of the ions through rolling process. The ions are moving and passing from one place to another by rolling through the medium. Okay. When we talk about the H plus or OH minus ion, their conductance is slightly different. They go through hop jump mechanism. If we are going through hop jump mechanism, then your hydrodynamic radius is not actually involved. Your conductivity cannot be just by the solution. We have to look into what type of electrode system which we have. Depending on that, we can depending on the movement of the ions, we can predict whether the mobility is going to be high or conductivity is going to be high. If the mobility is high, conductivity is high. Conductivity here I am talking about either the molar conductance or the specific conductance kappa. So, H plus and OH minus, both the values of conductivity is high and mobility is high, and the reason being the movement of the ions not by rolling through the solvent medium, but by the hop jump mechanism. We will take into the Grotthuss mechanism. I am going to show you how the hop jump movement of the H plus ion and OH minus take place. Before that, I would like just to mention the certain things which is important when you are talking about the electrolyte. What is the type of electrolyte mean? When we nomenclate various types of electrolyte, when we come across further discussions, you will say that there is a 1,1 electrolyte, 1,2 electrolyte, 2,2 electrolyte. What does that mean? When you have a say species which is going to give rise to some electrolyte species which has a Z charge number and nu as the number of ions which is going to be there in a chemical the formula unit of that particular species is gives you the nu, and nu and Z decide the type of electrolyte we have. When suppose you have Z equal to 1, then the Z plus minus is always taken as modulus, because we do not want any negative term associated. So, the modulus term gives you the Z value, the Z value is taken as a modulus term. So, 1,1 electrolyte is, suppose I have Z equal to 1, and here what you have is Z plus and Z minus, both are equal to 1, then we say it is a 1,1 electrolyte like KCl. When we have 2,2 electrolyte, then the generated ion, sodium ion, plus ion and minus ion, both are going to have a value of 2, like magnesium sulphate, sodium sulphate is barium sulphate. These are the two examples. And then if you have 2,1 electrolyte, means the cation is going to be 2, anion is going to be 1, then you have barium chloride type. And when you have say sodium sulphate, then sodium sulphates you have some Z value, Z equal to 1 and the anion is going to be 2. So, this type of electrolyte can be given to considered as 1,2 electrolyte. Okay. And when we talk about the mobility and conductivity, they have to be related. Mobility, molar conductivity is proportional to ionic mobility. So, the molar conductance lambda is nothing but Z equal to Z U F. U is the mobility, F is the Faraday constant and Z is the number of charge associated with the ion. For solution in a limiting dilution, when we are tending towards limiting value means concentration molarity is tending towards 0. From Grotthuss law of independent migration of ion, we can represent the molar conductance of each of the ions will be the representation of the total number of formula the formula units which can have for that particular ion into that of the cation plus that of the anion. So, hence we can rewrite the molar conductance instead of here we can write the capital. The molar conductance at infinite dilution is nothing but nu Z U with a plus and a minus sign multiplied by F. Okay. So, if in a special case, if Z1 Z plus and Z1 is Z minus equal to Z, they are equal values, then this expression simplifies to further U plus U minus ZF, right. Thank you.